Okay, so let's see, trying to see if you can see the PowerPoint. All right, so can everyone see the PowerPoint for chapter 6? Okay, all right, good. So today we're gonna start a chapter 6. So chapter 6 and 7, that is the last unit. The good news is with chapter 6, you can use quite a bit of the calculation using the interval, okay? So we're gonna talk a little bit later in using the calculator. So chapter 6 and chapter 7, there's something a little bit similar for the population and the sample. So we will find a confidence interval for the population. We also want to find a confidence interval for the sample. So we have two different type of the confidence interval, okay? So the first one, we're gonna have a confidence interval for the being. For the being, sigma is unknown, okay? I don't know, anyone still remember sigma? What is sigma?
The standard deviation?
Yes, very good. From which one? So it's the standard deviation for the population, okay? Sigma is the standard deviation from the population. If we have this little x, this is for the what? Sample standard deviation, okay? So since this chapter, we're gonna need to identify the sample or population. So that is very important that you recognize the symbol, okay? Sigma is the standard deviation for the population. Little x is the sample standard deviation. Remember, anything looks and sounds like a Greek is for the population, okay? Anything like sounds and looks like a little bit like more similar to the English alphabet. That's for the sample. All right, so that is one thing you kind of have a little bit of idea in here. So first, we want to find the point of estimate and the margin of error. Okay, construct and interpret a confidence interval when sigma is known, and how to determine the minimum sample size. When it's required to estimate the population mean. So basically, that is the objective for this section. Point of estimate for the population. So what is the base point of estimate for population mean? Remember, for the population, the mean we're using the mean, right? Anything looks like a Greek is for the population. If with the sample, we're using bar, X bar. So X bar is the sample mean. All right, mean is the population mean. Okay, so we're using the parameter to describe the population. We're using the statistic to describe the sample. So those are still a value in here. All right, so what is the point estimate? If I want to say, what is the household income for the entire city of Fort Worth? Okay, and if I don't have time to go to survey every household for the entire city, I might be able to choose a sample, right? A good sample as the sampling technique we used before. So if I choose a good sample for like a 100 household, all right, and if I calculate this 100 household income, and then we're gonna this 100 sample of the household from the Fort Worth city gonna be able to represent the entire city, the household income. If I choose the sample scientifically, right? So that is the purpose for this kind of point estimate for the population mean. So what is the base point estimate for the population? We can choose the sample using the sample bin, okay? If I choose my sample correctly, and this sample bin will be good for the population, that kind of thing, that way. All right. Trying to let people in here. All right. So if you can please mute your microphone until you want to talk, that'd be great. All right. So that way we don't have too much noise. Thank you. All right, so the point of estimate for the population is using the sample. All right, so using the sample in here. So this one, look at this one right here. A research is collecting data about a college athlete conference, and it's a student athlete. So this is random sample. Look at that, random sample of the 40 student athletes is selected, and their number of hours spent on required athletic activity for 1 week are recorded. So look at this one right here. So you can have from 19 hours all the way to 21 hours to 24 hours and so on, right? So this is a sample of the 40 student athletes. Okay, we want to use this one for the point of estimate for the entire population mean. All right, so if we choose this 40 sample correctly, okay, according to the sample technique we used before, and these 40 sample of the student athlete gonna be able to represent the entire population. So that is what we're talking about here. So you can add all this into the calculator, input into stat, and then go to the one variable state to do the calculation. Or you can simply just add a sigma of the x, right? And then divide by n in here. So that is the average is about 21.1 hours. Okay, about 21.1 hours for the 1 week practice. All right. So that is the point of estimate is using the sample mean. Next one, we want to look at the interval estimate. So an interval or a range of value is used to estimate a population parameter. Okay. As we said earlier, when you use a sample, you always have an error. Okay, because we don't use everyone. So even you choose 40 student athlete trying to represent all the athlete, right? Maybe thousands student athlete that way. So it will still involve some kind of error. All right. So before finding the marginal error of the interval estimate, first determine how confident you need to be that your interval estimate contains the population mean. All right, so for example, I'm gonna still using my forward the forward household income. Okay, and then I said earlier I choose n equal to 100, and then if I have my sample mean is 65,000. Okay, so for example, if I choose 100 household to do the survey, and then household income in the entire forward cities for this 100 sample, the average is 65,000. All right, how confident am I about this data? Okay, and then what is my margin of error? Okay, so if I say I'm 95% confident, all right, since I'm using the sample, so I cannot be 100% confident. So you can be 95% confident, or you can be very high, 99% confident, or you can have a 90%, or you can just have an 80% confident, or you can have anything else you choose. Okay, so this is called a confidence level. We're using C for the confidence level. All right. Since my sample 100 is not too big, not too small, so I'm gonna say I might have about 95% confident. Okay, so what does 95% confident mean? That means I might have a 5% error in this case. Okay, so that is the confident because I'm not 100% confident. Say, using the population, the sample, the population mean will be exactly 65,000. All right, so I'm gonna say like about 95% confident. Okay, so that is the level of the confidence. Okay, that level of the confidence, that means we have this confidence that the estimate the interval you estimate will contain the population parameter. Okay, so that means if I have an interval, that means between 64 to 66, right? And at least between 64 to 66, that is called an interval. Okay, so what's the interval in here? Interval is kind of like a, if I have an x greater than 64,000, right? Less than 66,000. All right, so this is 64K, this is 66K, and then my 65 will be right here, right? So that is called an interval, okay? Interval in here. All right. So if you have an x greater than 1, less than 3, right? That is the interval. Okay. So we have a 0 right here. We have a 1, 2, and 3. So between 1 and 3, that is the interval. Look at it. And then we write down 1, 3. So that is the interval in here. All right. So that is the interval in this case. So if I use C equal to 95%, and my interval is between 64,000 to 66,000. That means I have a 95% confidence that this interval, or the real population, entire population household income will between, will be inside this interval. All right. So that is this one right here. Of course, if you choose a large number, if I instead of choosing 100, if I choose 500 household, right? And my confidence actually will go up. Okay. So the larger sample size actually is the better. All right, so that is this one we call a critical value. Okay, critical value is the value that separates sample statistics that are probably from the sample statistics that are improbable or unusual. All right, so what does that mean? So if I have a C equal to 95% confident, okay, so that means I have a 5% not confident, or 5% error, okay? Usually we're using the alpha to represent the error. We're going to talk about it next. So alpha, so this is kind of error, okay? My error here will be 5% if I have a 95% confidence. All right, so how do I find this critical value, which we're going to using the Z-score, okay? The C here is 95%, okay, for example, and 95% is in the middle, all right? So from here to here, this entire bell curve middle part will be 0.5 or 95%, right? And how much is this tail? We call this is a right tail, and then we call this one is a left tail, okay? So if I make my 95% in the middle, I have two tails. Each one will be 100 minus 5%, 100% minus 95%. That will give you 5%, right? But since this is a symmetry, so the left and right are equal, all right? So I will using the 5% divided by 2. So each tail will be 2.5%. So each tail here is 2.5%. All right, so that's why, how do you calculate this tail area? Is 1/2 1 minus C. Okay, so that is how they come from. Okay, so if I use 95% confidence, as I mentioned earlier, this is 0.95, and then you have a 1 minus 0.95, right? 1 minus 0.95, we're giving you 5% or 0.05. If you're using the 0.05 divided by 2, you are giving you the 0.025. Okay, and how much is the Z-score in here? Well, if you go to use the calculator, you can look at the area to the left, right? We talked that last time. Area to the left. So this area to the left is 0.25, okay? And let me go ahead showing you the calculator. If you still remember how to use the calculator to find the backward, it's the second bars, okay? Go to the number 3. It's called inverse norm, right? So if I have an inverse norm and then I have an area is 0.025, and then my area is to the left, okay? So the default, usually area is default to the left. And I hit enter, okay? And that's how I get a negative 1.96 if I run to 2 decimal point. Okay, so that is negative 1.96 in here. And then if you go to look at this area to the right, since this is a bell curve, is symmetry. So if this is negative 1.96, this side will be positive 1.96, okay? I can also show you if you have a current version of the calculator, look at that. I can input, say this is 0.95, right? 0.95, and then, 0.95. I don't really have to go to calculate the tail, okay? I just said this is the area in the center, okay? This is the area in the center and I pass. But if you do not have this interface, the default is to the left. All right. So look at this one right here. I put this in the center. Now it's giving you one of them is negative, one of them is positive, right? And both are exactly the same number. Okay. So the left side G-score is negative, the right side G-score is positive, and they're exactly the same. Okay, so that's another way you can look at, you call a critical value. Okay, so and then we're going to talk a little bit critical value later as well. Okay, so sampling error, yes, the difference between the point estimate and the actual population parameter value, that is the sampling error, right? And as I said earlier, I want to find the entire city of Fort Worth household income. But if I only choose 100 household as my sample, this sample household income might be a little bit different than the entire population, the real average, right? So that is called a sampling error in here, okay? All right, so the next thing here is how do we find a sampling error? All right, there's a formula in here is called a margin of error, okay? So sometimes we call this is a maximum error of the estimate or error tolerance, okay? And this we using, most of the time we just call the margin of error. So this margin of error will determine how confident you are, okay? G sub C is a critical value, and this critical value is connected to the confidence level, all right? So the margin of error will proportion to the confidence level with G-score and the population standard deviation, and then relate to the N in here. So guess what? If my N increase, if everything else, Z and sigma stay the same, and then my sample size increase, my E actually decrease. Okay, so that means the larger sample size, the smaller the margin of error, which is makes sense, right? So that is this one right here. Okay. So this one is trying to estimate the margin of error. If the sample did not say it's normally distributed, usually we say sample size is large enough. So how large is large enough? If N is 30 or above, if N is 30 above, you know, that is enough sample size. We can say this is approximate, okay? If the question tell you, say this is normally distributed, that's perfect. But if it didn't tell you, but the N is 30 or above, we can say this is approximate, the normal distribute. Okay, so now we can using the bell curve. All right, so you can use the bell curve for all those good things we learned earlier to do the calculation in here. Okay, so let's look at this one right here. How do we find the margin of error? Using the data in example 1 and 95% confident label to find the margin of error for the mean number of the hours spent on required athletic activities by all student athletes in a conference. Assume the population standard deviation is 2.3 hours. So that means this one is sigma is 2.3, right? And then we want to find the margin of error. So this one you have to remember the formula is G of C times sigma over square root of N. All right. And then we already know N, it was 40, right? That one, N was 40 in here. And then how much is G sub C? Well, G sub C is come from the 95%. C is 95%. All right. And then G sub C for C is 95% is 1.96. So how do I calculate my margin of error? I just plug it in. Okay. Plug it in here. And then this is divided by square root of 40. And of course, you can go to use the calculator to calculate this one. If you put everything into the calculator, let me go ahead showing you how to use the calculator in here very quick, right? Okay, so we have 1.96 times 2.3, right? If you want, you can just go ahead calculate this first and then just hit divide, and it will carry the answer divided by this one. Okay, so you don't have to type the answer in here. Just hit divide, and then the square root here is second square is the square root. Okay, and then we have a 40, and then you hit enter. So that's, we are giving you 0.7 if you just round to 1 decimal point. All right, so that is called a margin of error in here. Okay, so now you have a 95% confident that the margin of the error for the population mean is about 0.7 hour in here. All right, with 95%, the margin of error will be 0.7 hour. Okay, let's see. Any questions so far? Anyone has any questions? All right, so if you look at let me go ahead and open the table in here. Okay, so if you go to look at the table, which I think I posted somewhere in there. If not, I can repost it again. All right, so if you go to look at this table, okay, you have a G-score, and then in here, you have this critical value in here. Look at it. These 4 labels are the most popular or the most common used confident label. All right, so we have an 80% G-score, the critical value will be 1.28. 90% confident label G-score, the critical value will be 1.645. 95% G-score is 1.96. 99% G-score is 2.575. Okay, of course, one is positive, one is negative, just like this bell curve on both sides. All right, so if you have one of these 4 numbers, you can come to the table and look at it to use it directly. If you don't, you can draw a bell curve and calculate on your own. Okay, I just showing you how to find this from the calculator. All right, so how do we constructing a confidence interval for the population mean? Well, first you have to look at like this is normally distributed or not. If not, you look at the sample size to see if it's greater than or equal to 30. So this is our kind of golden number, right? And then we need to find a sample mean X bar, okay? After you find the X bar here, you find the margin of error. All right, so the interval here would be using the sample mean minus the margin of error on the left side. The right side is using sample mean plus the margin of error. All right, so look at this one right here. We just found the margin of the error was 0.7, right? And then the X bar the sample bin was 21.1. So now you have on the left side, you have X bar minus E. So you have 21.1 minus 0.7, giving you 20.4. On the right endpoint, you have a 21.1 plus 0.7, so giving you 21.8. And then we usually put this whole thing into the parentheses. So 20.4 and then comment 21.8. So the smaller number, okay, smaller number on the left side, and then the larger number on the right side. And then that is the confidence interval in here. Okay, that's the whole thing. That's the confidence interval. All right, so mu is greater than 20.4, less than 21.8, right? So you with 95% confidence, you can say the population mean number of the hours spent on required athletic activity is between this one, okay, between 20.4 to 21.8 hours, that one. And also we have a 95% confidence that this interval will include a population mean. All right, so let's look at this one right here. How do we do this one? Okay, so that would be the key for this section. Constructing a confidence interval. All right, if a college admission director wishes to estimate the mean age of all students currently enrolled, in a random sample of the 20 students, the mean age is to be 22.9 years. From the past study, the standard deviation for the population is 1.5, right? And then we're gonna, this telling you the population is normally distributed, okay? You want to construct 90% confidence interval for the population age. All right, so remember the confidence interval, we're gonna have a X bar minus E, all right? And then the right side is X bar plus E, okay? And I already have an X bar here. They said a sample bin for 20 students is 22.9, okay? 0.9 years. And the sigma here, standard deviation for the population, sigma here is 1.5, all right? My C here is 90%. All right, so what does this C mean? That means I can find a critical value to calculate the margin of error. So we giving you that earlier, right? I just showing you this one, 90%, I can use my G sub C here is 1.645, okay? 1.645. All right, if this is not in there, how do you calculate? Well, you drop a little bit bell curve, okay? So you have a 90% in the middle, look at it. 90% or 0.90, C is in the middle, right? And then this is G sub C, this side is negative, this side is positive, all right? I can just go to do my inverse norm. So this side, if this 1 minus C will be 0.1, right? 1 minus 0.9 will be 0.1. And then this is 1 minus C divided by 2 for each side. 1 minus C divided by 2. So 1 minus C is 0.1. So this will be 0.05, 0.05. All right. So you can go to look at the calculator for the G-score if the number is not on the table, right? So go to second bars, second distribution, and then you use number 3, inverse norm, all right? So I change this one into 0.05, and then I'm gonna switch and say this is my left side. All right, if I do this one right here, I'm gonna get a negative number. But that's okay. If I round to 3 decimal points, it's negative 1.645. Okay, so that is, and we choose this one to do the calculation. We always plug a G-score as positive because we have one side is minus E, one side is plus E, right? So we're gonna just calculate one E in here. So my E here is G sub C times sigma over square root of N. All right, so that's 1.645. times sigma here is 1.5, divided by square root of n is 20, right? So that is this one in here. Okay, so you can put this whole thing into the calculator. So if we want to 1 decimal point right here, this is about 0.6. Okay. And then my x bar is 22.9. So we're going to have a 22.9 minus 0.6. And then the other side is 22.9 plus 0.6, right? 0.6 right here. Okay, so this will be 22.3. This at a 0.6 here will be 23.5. So my interval here will be 22.3 to 23.5. All right, so that is my interval in this case. Okay, so what does that mean? That means we're gonna have a 95% confident that you said the mean age of all the students for the university is between 22.3 to 23.5 years old. Okay, so we just repeat a different thing, find a confident interval for the population mean. The good news is if I don't want to calculate this one by hand, guess what? This entire interval will be able to find it from the calculator. Okay, but one thing is sometimes it didn't always ask you to find the entire interval. Sometimes it might just ask you to find a critical value, z-score, right? Sometimes it might just ask you to find a margin of LE. Okay, so if you know how to find a z, how to find the e, you just plug it into the formula. You can find the interval easily. But if you just want to find the entire interval, there's one way that you can do the entire thing from the calculator. So that's what I'm going to show you. Find the entire interval from the calculator. All right. So we're gonna go to stat, test. All right. Remember, we're using stat edit before. We're also using stat cal before to do the linear calculation of one variable statistic, right? This time, the last two chapter 6 and 7, we're gonna have a test. Okay, so the last chapter, we're gonna have a hypothesis test. So you have a z test, a t test in here. But the chapter 6 is the interval. So we're gonna have a z interval and a t interval. All right. If sigma is given, that's for the population, that would be the z interval. All right. So you can have a raw data or you can have a state. Usually when the question giving you the sample mean, you will have a statistic already. You have a state in here. So if I just type everything in here, right, my sigma here is 1.5. Okay, so my sigma here is 1.5. Okay, my sample mean here is 22.9. Okay, and then my sample there was 20. Okay, and my confidence interval, we have a 90%, so 90% is 0.9. All right, guess what? I just input all these things and say calculate. Okay, so look at this calculation in here. Look at it. We have this calculation. We have a 22.3. Look at it. If I round to just one decimal point, the next digit is 4. I round it down, right? So I have a 22.3. And then this round to one digit decimal point, this is 5. Second digit is 5. So you round up. So we have a 23.5. Exactly the same here. Okay. So now you can see using the calculator is so easy to find the entire interval. All right, so let me repeat one more time. You will go to stat and then go to the test, and then we want to find a z interval. So it's number 7. Okay, you can cursor it down or you can just type a 7. All right. And then if you have a raw data, you're gonna just input into L1 and you can use the raw data. If you already got a sample bin, you just hit a stat in here, input you population, standard deviation, input your sample bin, input your sample size, and input your confidence label, and then you just calculate. And this, we are giving you the entire interval. All right, very cool. So that is this is section 1 in here, okay? All right, so how do you interpreting the result? How do you explain your final outcome? Sometimes, you know, people will say there's 90% probability that the actual mean is in the interval. No, that is not a correct way to say this kind of statistical outcome, okay? So the correct way here is say, if the large number of the sample is correct and the confidence interval is created for each sample, that means appropriate, okay, that is a condition, right? So basically the entire thing is you have about 90% of confidence that this interval will include the population mean, all right? So that means you 90% of confidence that the interval will include the population mean. That is the correct way to say, okay? All right, so what is 90% confidence? So you can see my interval in here, right? So the first one, the interval from here to here, and the population bin is in here. This is my sample bin, all right? My sample bin is in the dark. And this is a population bin. I have a red line, red vertical line. This is a population bin, right? So this one, this first interval, it does include a sample bin. The second interval also include a sample bin, right? Which interval did not include a sample bin? Or this interval, okay? Because I only have a 90% confidence, all right? That the interval will include a sample bin. So that means 9 out of 10 interval will include bin. So this 9 out of 10, one of them is not. All right, so another thing for this section here is about the sample size. Okay, this one, look at it. If I have a E here is equal to G sub C times sigma over square root of N, right? If we're giving you the margin of error, can you find a sample size here? The answer is yes. So these two formula, these two actually is from the same formula. All right. If I multiply both sides by square root of N, okay, and then I will have a G sub C times sigma, right? And then I divide by both sides by E. Look at that, I divide by both sides by E, this cancel out. And then I will have a square root of N equal to G sub C times sigma over E, right? And then if I want to solve for N, that means I have to square both sides. I will have to square both sides. And then square root and square cancel out. So that's why I have E equal to G sub C times sigma over E squared. Okay, so you don't have to go through all these steps to find the N, because this N is also in the formula C. Okay, so the reason I shown that to you is trying to let you know that this N, the N and E, these two formula actually is the same formula. Okay, so that means if I giving you the N, giving you the sample size, you can find the margin of the error, right? But on the other hand, if I giving you the margin of error, you can find the sample size as well. Okay. All right, so let's look at this one right here. If the researcher in the example 2 want to estimate the mean number of the hours spent on the required activity by all student athletes in the conference, how many student athletes must be included in a sample if you want to be a 95% confident and the sample mean is just 0.5 hour of the population mean? Okay, so that means I need to find the N, okay? How many student athletes? So I need to find the N, and then this will be G sub C times sigma over E. And then remember, you have to square them, okay? And then we said a 95% confident the G sub C is 1.96, all right? So we have a 1.9, 96 times sigma. All right, so let's see how much is the sigma we have earlier. The sigma we have earlier, I think it was 2. Table 2. All right, so this sigma here is 2.3. Yeah, 2.3 in here. Okay, so we have at least 2.3. And then we want the sample, the margin of error. Okay, this is is within 0.5 hours, so that's the E. Okay, margin of error will be 0.5, and then we square them. Okay, so we're gonna go to calculate this one. So how do we calculate this one? You plug it into the formula. Okay, so make sure, remember, you have to square. So 1.96 times 2.3 divided by 0.5, and then close parenthesis, you square it, right? And then you have a 81.288 something. Okay, so we have a 81.288. All right, so sample size, we want to run to the integer because this is number of the people. Okay, this is number of people, of student, of people here. So all these sample size, we have to be in the integer. And in order to get enough sample size, we always need to round up. Okay, if you don't exactly get exactly 80 or 81 or 82, if you have anything decimal point in here, you always round up. So this is called a spatial rounding. Spatial rounding. All right, what does a spatial rounding mean? Always round up. So instead of 81.2 something, I need to round to 82. Okay, so my minimum here need to be 82. Otherwise, you won't be able to have a 0.5 hours of the error. All right, so 82 will be the minimum one. Always round up. Even you have a 81.001, you still have to round to 82. Okay, so this one is not a regular rounding. Regular rounding is 5 or above, you round up, 4 or below, you round down, right? But this is called a spatial rounding. So you always need to round up in here. All right, so that will be our fourth section for chapter 6. Any questions so far? Anyone has any question? Okay, so that is 8.1. I'm sorry, not 8.1, 6.1. Okay, we want to go ahead and introduce another section here is 6.2. Okay, 6.2 here is the T distribution or the T distribution table. So T is called a student distribution. All right. Sometimes the T distribution is called student because it was discovered by a graduate student. All right. So we want to construct the interpol, the confidence interval for the population when sigma is unknown. All right, so what is the sigma is unknown. The fourth section we have here is giving you the sigma, right? When sigma is given or sigma is known, all right, we're gonna using the called Z interval, okay? And this section sigma is unknown. All right, and then we're gonna using the T interval. Okay, so we do have 2 intervals to use in here. All right, so the challenging part for this chapter is trying to figure out which interval do you use. Do you use Z or do you use T interval? Okay, so that is one thing. The common thing for this chapter and the next chapter is similar is in here. When sigma is given, you're using the Z interval. And then for the hypothesis, if sigma is given, you're using the G test. Okay, we're gonna next chapter, we're gonna have a G test. And then when the sigma is unknown, you're gonna using the T test. All right, so we have 2 different tests the next time for the next chapter. So that's the common thing for this chapter and the next chapter. All right, so how do you find a t? Usually when you find a t, sample size is a little bit smaller, a little bit less than 30, okay? So when the sample size is less than 30, a lot of time we're gonna using the t interval, okay? So t number, t score, remember how you find the z score? The z score is x bar minus mu over sigma divided by square root of n, right? That's a z score value, not a critical value, but a regular z score. And then the t score, t distribution is similar to the z. Look at it. So this is x bar minus mu. Instead of using the sigma, you're using the sample standard deviation using x. The rest is the same. All right. The only difference here is for the z, you're using sigma. For the t, you're using x. Okay. But these two formulas are pretty similar in here. All right, so we're going to introduce a little bit t distribution. The mean, median, mode for the t distribution are also equal to 0 for the standard one. And the t distribution is also similar to the z. It's also bell-shaped. Okay. It's also bell-shaped and symmetry. All right, and symmetry. Okay. The total area under the t curve is also 1. All right. And the tail for the t distribution usually is thicker than the standard normal distribution because the sample size is smaller. So this bell curve usually a little bit far away from the horizontal line. All right. So that's called a little bit thicker. So this one is a little bit thicker. That's what we're talking about, a little bit thicker in here. All right. The standard deviation for the t distribution value is the sample size. Okay. So we have called the degree of the freedom. All right. So degree of the freedom is using m minus 1. All right. Using sample size minus 1 in here. Okay. So the t distribution is a family of the curve, each determined by a parameter called the degree of the freedom. All right. So degree of the freedom, we're using df. This is the number of the free choice left after a sample statistic such as x bar is calculated. All right. So the t distribution, the degree of the freedom is always using sample size minus 1, or 1 less than the sample size. Okay. So df is m minus 1. All right, this is giving you a little bit bell curve to see why the n is when n is smaller, right? When n is smaller, df is also smaller. Okay, when n is smaller, df is also smaller because df degree of the freedom is n minus 1, right? So look at that. This df is equal to 2. That means n is 3, right? And this curve is far away from the horizontal one. So this one is called thicker. All right. And then when you have a df equal to 5, this sample size is a little bit bigger. All right. So this one is a little bit thinner than df equal to 2, right? And then you can see this blue one is a normal curve. Normal curve usually n is 30 or above. So that is this kind of comparison. Okay. All right, we also need to know how to read the critical value from the t table. Yes, we have this t table in here. So look at it. If I have a sample size is 15, the confidence level is 95%. Okay, so we need to find a df n minus 1, right? df n is 15, so 15 minus 1, that would be 14. And then C here will be 95% or 0.95. So we will go to the T table. All right, let me open the real table in here. So we have this T table. All right, so we have the table 4. That's the standard normal distribution. Now we're gonna read the table 5. Okay, so table 5 here is called T distribution in here. So we have a degree of the freedom is 14. Okay, df is 14. When n is 15, my df degree of the freedom is 14. My confidence level, what is my confidence level? It's 95%. Okay, so 95. So look at this level of the confidence. C is 95%. So I have this corresponding to this one. This will be 2.145. All right. So that is the T distribution with 95%. Okay, so look at this one right here. Yeah, we do have this one right here. Okay, look at this one. We have a 0.95 and then 14, so that's corresponding to 2.145. All right, so that is how you do your critical value from this T table or table 5. If we want to find a confidence interval, it's very similar. Okay, we do the confidence interval in here. Okay, so step 1, we have to look at is this G or T interval. If sigma is unknown, all right, if sigma is unknown, we're gonna using the T interval, okay? And then the sample size usually, you know, when the sigma is unknown, we're using T, right? So we find the X bar in here, we find a sample standard deviation. You can use this one from the calculator. You can find the sample standard deviation and the sample mean directly, both directly from the calculator, all right? And then you need to choose the degree of the freedom is n-1. So you can read the T sub C in here, okay? After you find the T sub C, you calculate the margin of the LE, and then the interval will be X bar minus E and then X bar plus E. So this is the same formula as you have in a T interval. Okay, so let's see how do we do this one in here. You have a randomly select 16 coffee shop and measure the temperature of the coffee shop at each one. The sample being the temperature is 162.0 Fahrenheit with a sample standard deviation. Look at it, this is a sample standard deviation is 10. All right. You want to construct 90% confidence interval for this coffee shop. Okay, assume that this is normally approximately normally distributed. Okay, so how do you do this one right here? So step one, the challenging for this one is this a G or T interval? And why? You need to know why, so next time you won't make mistake. Okay, so is this a G or T interval? Anyone? It might be a little bit challenging at the beginning, right? So since we just start learning this one, but this one is a T interval. This one is a T interval. Why this one is a T interval? Because sigma is unknown. Sigma is unknown. Look at it. So that's why we have to know this standard deviation is from the sample. Okay, this is a sample standard deviation. So this is X. This is not a sigma. Okay, not a sigma in here. So sigma is unknown. All right. So and then we look at the n here is only 16. So we're using the T interval. Okay. Usually the sample T interval sample size usually a little bit smaller. All right. So we want to find the confidence interval. So we still using X bar minus E and then X bar plus E, right? So we already have an X bar here. X bar here is X bar here. Okay, so we have an X bar here is 162.0 degree Fahrenheit. All right, so I need to go to find the E. So my E here is T sub C times X over square root of N. All right, so we have to go to find the T sub C for what? For 95%. Okay, so confidence is 95% or 0.95. my n here is 16, so I need to go to using the df. Since we want to find a t interval, so we're using the degree of the freedom is n minus 1. So 16 minus 1, that is 15, right? So we need to go to reader. So all this thing right here is trying to find a t sub c, okay? So let's go to the table to look at the t sub c in here. So we have a df is 15. Okay, so let me go ahead and erase this one so you don't get confused. So we have this is df is 15. All right, 15 in here. Okay, and then confidence level is 95%. So that should be this one. All right, so we have a critical value is 2.131. Okay, so we have this is 2.131. All right, so now we can plug this one in. Okay, 2.31, and my x here is 10 degrees Fahrenheit, and then divided by square root of n here is 16. Okay, so don't forget, don't confuse your n and df. All right, so square root of 16 will be 4, right? And then this will be 21.31 times 10. All right, so if I go to divide by this one, approximate into decimal point, this is about just 5.3. So now we can find the interval. Okay, so we have calculate. We calculate. Actually, this is the second step. We find a critical value. Third step here, we find the margin of error, right? And then the step 4, we're gonna find this interval. Okay, interval. So x bar here is 162.0 minus 5.3. Okay, this side will be 162.0 plus 5.3. All right, so mu will be greater than, go to use the calculator. So this is 156.7, this will be 167.3. If I write down my interval notation, this is my interval notation. Okay, so that is how we calculate the interval for the sample, okay, using the t interval. All right, so what does this mean? This means with 95% confidence, you can say the mean temperature of the coffee shop is between 156.7 to 167.3 degree Fahrenheit. All right, so that is do this whole thing by hand, okay? The one good thing here is you can do this whole thing in a calculator. Okay, so I'm showing you both ways. One is doing it by hand and another is doing by calculator. All right, so how do I find the entire interval by the calculator? Well, go to stat and then test. And then remember, this time is choosing number A, is choosing the t interval, okay? This is the one you have to make a decision. Calculator won't tell you. You are the one have to choose the correct interval, okay? Same thing, since I already got a sample bin, so I'm going using the state here, all right? So stay here, this is 162.0, it's just 162. Sample standard deviation is 10, sample size is 16, and then we want a 95% confidence. So I have a 0.95, and then I just go ahead and hit calculate, okay? So look at that, when I calculate this one right here, if I run to 1 decimal point, right? I have a 156.7, this is wrong to 1 decimal point, this is wrong up. So you have 156.7, this is the second digit wrong down, so you have 167.3. We have a match here. All right. So that is to do this whole thing by the calculator. And the reason I want to show you step by step here is sometimes it might not just ask you the entire interval, right? Sometimes it just asks you to read a critical value. Can you read this critical value? And the answer will be yes. This is just reading the table, right? Just make sure you have a df equal to n minus 1, okay? And then sometimes it might just ask you, oh, just find the margin of the error for this one, okay? So it's not always test you the entire interval. This question I can break down into 3 different smaller questions, right? One question will be just to find the critical value. Another question will be just to find the margin of the error E, okay? And then of course, one question you can ask for the entire interval. All right, so that is this one, pretty similar to the Z interval, but the reason you use this one right here is, look at this one right here. The normal or the T distribution, the normal distribution is the Z, okay? When we say normal, that is the Z interval. All right, T distribution is the T interval, okay? So how do we identify here? If the population is normal distribute, or if you didn't say normal distribute, if your sample size is greater than or equal to 30, and the sigma, you cannot use the standard normal distribution or the T distribution. Okay, so basically you have to have enough sample size, or at least it's normally distribute or approximate normal distribute still work, right? That kind of thing. And then the key thing here is, do you use Z or T? If sigma is unknown, sigma, is known. The answer, if it's not, that means unknown, right? You're using the T distribution. If sigma is known, the answer is yes. Now you're using the Z distribution, Z interval in here. Okay, so that means this is sigma. That's why I asked you earlier. It's very, very important for the sigma in here. All right, so look at this one right here. If we don't ask you to calculate, just ask you to use the Z or T interval in here. So let's read this one and then try to see if you can figure out the answer in here. We don't ask you to do the calculation. Is sigma known or not? Is sigma known or not? Okay, so you randomly select 20 newly constructed houses. The sample mean of the construction cost is 181,000, and the population standard deviation is $28,000. Assume this cost is normally distribute, right? Should you use the normal distribution, T distribution, or neither? If you want to construct 95% confidence interval for the population mean of the construction cost. All right, so it's a Z or T interval. Z or T interval. Anyone? All right, let me see a little bit respond here. Can chat. Some people said Z, some people said T. So let's look at this one very carefully. When sigma is known, so that's why I ask you, what is sigma? What is sigma? What's sigma mean? Sigma means what? Population standard deviation. Okay, so did this one telling you the population standard deviation? Okay, look at that. This one, it did tell you population standard deviation in here. So sigma is known. Sigma is known. The answer is yes. Sigma is known. So this one should be a Z interval, not a T interval. Should be a Z interval because it did telling you the population standard deviation. All right, so a little bit tricky, yeah. That's why we have to look at what is sigma. Okay, sigma is the population standard deviation. If it's telling you, you're using the Z. If it didn't tell you, or this one is from the sample, now you use a T. Okay, so that is something you have to be very careful. The good news is this is all for chapter 6. So basically, chapter 6 we only require what? 2 sections. Okay. Chapter 6, we only require 2 sections in here. And then next one right here is the chapter 7. Okay, chapter 7 we have 3 sections. Okay, I probably just want to cover 7.1 only, not a 7.2. If we got time left. There's a little bit something similar for the chapter 7 and chapter 6, which is G or T interval, G or T test. They're using a similar one. Okay, so this is our last chapter. It's called a hypothesis test. All right, so where's the hypothesis test in here? Okay, so let's go ahead and introduce this fourth section because there's a lot of concept in here. Okay, a lot of concept in this fourth section. Hypothesis test basically is kind of, you can hypothesis test for pretty much everything. Okay, and there's so we have an introduction to the hypothesis test. When you do the hypothesis test here, you're gonna have to identify the known and alternative hypothesis. One is called known hypothesis, one is called alternative hypothesis, and then you're gonna encounter 2 types of error. One is type 1, one is a type 2 error. Okay, and then you're gonna have a 1-tail, 2-tail test. Okay, all right. So how do you write a claim of the hypothesis test? So there's a lot of concept on 7.1 basically. All right. Since we only have 2 weeks left, so I want to go ahead and consider to talk about this one right here. Okay. Hypothesis test is a process that uses sample statistics to test a claim about the value of the population parameter. Okay, so for example, if you consider a manufacturer that advertises a new hybrid car has been gas mileage of 50 miles per gallon, right? So you MPG, miles per gallon, for 50. If you suspect the bean mileage is not 50 miles per gallon, how can you show the advertisement is false? Okay, so that is the hypothesis test, right? We want to test a claim to see if this is a true or false. Okay, so if the company telling you, say, hey, my hybrid cars has a very high MPG, miles per gallon, right? And this one is 50 miles per gallon, so that's pretty high. And if you don't believe that, you cannot just tell the car dealer say you are lying, right? You have to provide evidence to prove the outcome is the statement is true or not. So this will be called a statement. Okay, the manufacturer advertises this one. In here, we call this is a statement. All right. Sometimes in statistics, in the hypothesis test, we say it's a claim. Okay. We want to test the claim to see if this claim is true or false. All right. So that is a hypothesis test, right? And then we can go to, if I want to test this is true or false, I will have to go to do a survey, right? So maybe I go to survey 30, hybrid cars and then test the MPG to see how many miles per gallon can each of the 30 cars have, right? And then I will be able to do my statistic analysis, and I'll be able to come back to tell the car dealer, say, hey, you tell the truth or you were lying, that kind of thing. Okay. All right, so that is the statistical hypothesis. It's a statement about a population parameter, right? And when usually you have to be very careful to state a pair of the hypothesis. So one is represent the claim, okay, or the statement. The other is called a complement, okay? the complement in this case. When one of the hypothesis is false, the other one must be true, right? So the complement, so this only have two outcomes, either true or false. If one of them is false, the other one must be true. If this one is true, the other one must be false, okay? So in hypothesis, we use called a known hypothesis and an alternative one, okay? So we're using the known hypothesis and the alternative hypothesis to represent, the original claim. All right. So with a known hypothesis, known is 0, nothing, or known is 0. So we're using the H sub 0 to represent the known hypothesis. Okay. The other one is called alternative hypothesis. We're using the H hypothesis. So we're testing the hypothesis. So we're all using H, right? The false initial. The alternative one, we're using the H of A. Sometimes you can write down this H of A or write down this one in here. All right. So this is a complement of the known hypothesis. So since known is always include 0, so we always have an equal sign. Okay. Less than or equal to, greater than or equal to, or just equal to. All right. So that is this one. The alternative one do not have an equal. Alternative one is always greater than, non-equal, or less than. All right. So this one, H sub 0, we call H naught or H sub 0. And then this one is reading H sub A. Some of the book, instead of using H sub A, some of the book are using H sub 1. Okay. But H sub 0 is always used for all kinds of book. But some of the book for the alternative, they're also using H sub 1. So they have a 0 and 1. Our book is using A for the alternative one. Okay. All right, so we have 3 pairs of the complement in this case. If I have a known here is less than or equal to K, my complement will be just greater than, okay? So they're always exclusive. If my known is greater than or equal to, my alternative one will be less than. And if my known is equal, my alternative will be non-equal. All right. So that means if you write down one of them, you can write down the other one. If you know giving you one, you can write down the other one. Okay. All right. So let's look at this one right here. Write each claim as a mathematical sentence, state a known and alternative hypothesis, and identify which represents the claim. Okay. So a school publicizes that a proportion of its students who are involved in at least one extracurricular activity is 61%. All right, so what does is mean in here? Is means equal, okay, equal. So you have a bin, so bin in mu is equal to 61%. All right, mu equal to 61% or 0.1 or 0.61. All right, so what's the alternative one? Since I have a known here is equal, the alternative one will be, look at this one right here. So we have this is 1 pair, right? 1 pair in here. We talked about earlier, this only got 3 pairs. All right, so I have a known here, mu is equal to 0.61. My alternative one will be non-equal to. Okay, the alternative one will be non-equal to. So that is this one right here. Okay, so you have a school public the proportion. Okay, proportion using P. Okay, P is equal to 0.61, and then the alternative one will be non-equal to. All right, and this one is the claim or the statement from the question, right? The question telling you the proportion is 61%. All right, so that is the claim or the statement from this whole thing. Okay, so let's look at the other one in here. Okay, this one is say a car dealership announced that the mean time for the oil change is less than 15 minutes. Well, less than is given. All right. So this one doesn't include equal sign. So since it didn't include equal sign, so must be going to the alternative one. And this is also called a claim, or sometimes the claim is also the statement from the question. All right, because the question told me said the mean time is less than, the mean time for the oil change is less than 15 minutes. So this is directly from the question. So that's the statement or the claim in here. Okay. And my alternative one will be mu will be greater than or equal to 15. Okay, because this is complement. So we always write down whatever the question tells us, and then we go to write the other one. Okay, so if you look at this one right here, let's see which one the question already tell you. All right, this is the company advertising that the mean lifetime of its furnace is more than 18 years. What does more than mean? More than 18 years. More, that means greater than 18 years. Okay, and greater than doesn't have an equal sign, so this will go to the alternative because the non always have to include a equal sign. So this is the claim or the statement from the question because that's what the question tells us. All right, so where's the alternative one? Alternative, where is the complement one? All right, so this is greater than, my complementary will be less than or equal to 18. All right, so you always need to know how to write down the known and alternative hypothesis, okay? This one is just so important because we need it later. All right, we do need this whole thing later on. Okay, so when we talk the the hypothesis, we always involve the two types of error. Okay, so that's why I said this chapter the concept is a little bit more. All right, no matter how hypothesis represent the claim, always begin the hypothesis test assuming that the equality condition in the non-hypothesis is true. So that means when you perform a hypothesis, one of the two decisions will be made. All right, so that is quite mouthful in here. I usually like to compare this type 1. We have a type 1 error and then type 2 error. So in statistics, you have these two types of error. Okay, one type of error said you reject a non-hypothesis. All right, or you fail to reject a non-hypothesis. Okay, so there's a possibility of making the wrong decision. So where's the wrong decision in here? Look at it. If we have a non-hypothesis is true, and you do not reject the non, so this is called a correct decision. But if the non-hypothesis is true and you reject the non, that means you against them, right? You against them, you make a type 1 error, okay? And if the non-hypothesis is true, you accept that. But the problem is in statistics, we don't want to use accept this word. We said do not reject or fail to reject, okay? When the non-hypothesis is true and you fail, you do not reject them, you say that's okay, that's the correct decision, right? And the non-hypothesis is true and you say that's not okay, you reject them, then make a type 1 error. All right, that is one type of error. The other type of error here is when the non-hypothesis is false. And then when it's false, you reject them, that's the correct decision. But when this is false, you do not reject them, then making a type 2 error. Okay, so that's two type of error in here. All right, I like to compare this type 1 and type 2 error with the core system. Okay, when you go to the core system, you have a judge, right? You judge say everyone is innocent until proved guilty. All right, so if a person is innocent and the judge let a person going home, okay, so that's the correct decision. But if the person is innocent, and the judge said, no, you're going to the jail. So that actually is called a type 1 error in here. Okay, you reject the innocent person, so that's the type 1 error. But when the person is not innocent, that means when the person innocent is false. So if the person is guilty and the judge said, yeah, you go to the jail, you reject the, you said when the person is guilty and the judge said you go to the jail, that is the right decision, right? But when the person is guilty and the judge did not reject them, the judge said you can go home. That is another type of error, called a type 2 error. All right. So you can kind of going through these two type of error with the court system, it kind of make a good comparison that way. Okay, making a good comparison. All right. Okay, so how do I identify type 1 and type 2 error? Basically, in this book, we only talk the type 1 error. We don't talk the type 2 error. We don't calculate the type 2 error. That will be for another statistic course, okay? So for this course, we only using the type 1 error. We're using alpha. Alpha usually is 5%, 10%, or 1%, okay? As we said earlier, if we have a confidence level is 95%, that means you are making a 5% error. Look at it, this kind of thing, all right? So that is the one we trying to find in this case, the type 1 and the type 2 error, all right? Okay, level of the confidence, that's the one we're talking about in here. So the level of the significance, basically, this is called level of the significance. So you maximum allowable probability of making a type 1 error with using the alpha. Okay, this is the lowercase of the Greek alpha. When alpha equal to 0.5, when alpha equal to 0.5, so that means you have a 5% of the chance we are making a type 1 error. All right. We're using beta for the type 2 error, but we don't really calculate the type 2 error in this chapter, okay? Because we are the fourth level of the statistics, so we don't calculate. We only calculate the alpha, all right? So alpha level is the probability of making the type 1 error in here, all right? And then we have alpha is 0.1, so that's 10% of the error, 0.5, 0.5, that's 5% of the error. This is 0.01, this is only 1% of error, okay? And we also have to make sure we have, we're gonna have a two test for this one right here, right? One is a G test, one is a T test. We're gonna ignore the chi-square test. We are not talking the chi-square test for this chapter, okay? So we're gonna have a two test, G and T test only, okay? All right, so this one is pretty similar. If sigma, giving you the sigma, if sigma is known, when sigma is known, you're using the G test, okay? When sigma is known, sigma is given, sigma is known, you're using the G test. In chapter 6, we use the G interval. In chapter 7, you're using the G test if it's a hypothesis test. When sigma is unknown, in chapter 6, we use the T interval. In this chapter, we're using the T test, okay? And we're gonna ignore the chi-square test later on, okay? So we're gonna have a p-value, which is the, p is the probability value in here, all right? So p-value is also the area for the bell curve, okay? So probability is part of the bell curve in here, all right? And then before we talk the hypothesis test, we're gonna talk the three different areas for the bell curve. One is left tail, right tail, two tail, okay? So what is the left tail, right tail, and two tail in here? So if you have look at it, if you have something is less than, okay, less than will be area on the left side, all right? So if you have a hypothesis alternative one, mu is less than something, less than is area to the left. So this is called left tail test. When you do the left tail or right tail, always look at the alternative one. Always look at the alternative one. Do not look at the non-hypothesis. Only look at the alternative one. Okay. So this one is less than, so that's a left tail test. All right. If this one mu is alternative one, remember we only look at the alternative one. If alternative one is greater than, that's the right tail test. So that you are testing the area to the right. Okay, so that's called a p-value. P-value will be area to the right in here. If you have this alternative one is non-equal to, all right, non-equal to this, we have a non-equal to in here, all right, non-equal to, that will be the two-tail, all right, so non-equal to can be either one part on the left, one part on the right, and each part will be half of the p-value, okay, each part will be half of the p-value, so that's the two-tail test. Okay, so let's go ahead and look at this one right here. Okay, so we're gonna put everything together in this case. Identify the left tail or right tail, and then we're gonna write down the known and alternative hypothesis. Okay, so a school publicized that the proportion of the students who involved in at least one extracurricular activity is 61%. Remember, we said this is write down the known alternative hypothesis is the proportion. Okay, the proportion. So I'm using P is 0.61. Okay, and then P equal to 0.61 should go into the alternate. Should go into the known hypothesis, because known is always has an equal. All right, and then this one will be non-equal because this has an equal. The complement will be non-equal, and this one is from the equation. So this is the claim. This claim has an equal sign. So your claim is in the known hypothesis. All right, and what kind of test is that? And remember, the test will look at the alternative one. So this is gonna be called a two-tail test. Okay, two-tail. So that means one part is on the left, one part is on the right. Okay, each part is half of the p-value, half of the p-value. So this is called two-tail test. Okay. All right, so that's two-tail test in this case. Okay, so let's look at this one again in here. All right. So a car dealer announced the mean time for the oil change is less than 15 minutes. Remember, we said that less than didn't have an equal sign. So less than, we are going to the alternative one. And this is also called a claim because that is the question tell us, right? And less than will be a left tail test, left tail test. And the left tail test is also called one tail because you just on the left or just on the right, that's all one tail, right? The only thing you have a two tail is you have a both tail. All right, so that's called a two tail. Okay, so left tail or right tail is called one tail. And my known hypothesis will be the complement. So complement for less than will be greater than or equal to. Okay, so that's how you write down a known and alternative hypothesis. Okay, actually it's quite straightforward, right? You write down whatever the question given to you first, and then go to write the other one. All right, so look at this one right here. The company advertised that the mean life of its furniture is more than 18 years. So more than is greater than. All right, and this is also called a claim. My claim here is in the alternative one because that's the question tell us, right? And then this is a right tail test because it's more than, greater than is more than, so it's on the right side. All right. And then this is a right tail test. It's also called one tail, right? And my known will be the complement for the greater than will be less than or equal to. Okay, so that's how you write down your known and alternative hypothesis in this kind of situation. All right. We're gonna have four different outcome in here. Decision rule based on the p-value. Okay. If we compare the p-value with alpha, when the P is less than or equal to alpha, you call reject the known hypothesis. When P is greater than alpha, you say fail to reject the known hypothesis. Fail to reject, sometimes we just say do not reject. These two are the equivalent statement. All right, so do not reject or fail to reject the known hypothesis is the same thing. Okay, so if you claim, that's why we have to identify where is the claim. If you claim, where's the claim? Claim is the statement from the question, right? If you claim is in a known hypothesis and you reject a known, that means you have enough evidence to reject a claim. If you fail to reject a known, that means you don't have enough evidence to reject a claim. If you claim is in an alternative one, which is a lot of time, majority of the time we have a claim in an alternative, okay? And you reject a non-hypothesis, that means you have enough evidence to support a claim. If you fail to reject or do not reject a non, that means you don't have enough evidence to support a claim. All right, so this one look very abstract at the beginning, but once we got an example, you're gonna be able to understand this table a little bit better. So we're gonna come back to review this later on, okay? When we go to the section 2 and 3, we're gonna come back to use this one and you will understand a little bit more later. All right, so right now we just need to be able to, using the table in here, look at this one right here. If you perform the hypothesis test for the claim, should you interpret the decision if you reject the non-hypothesis? Okay, so the claim here is the school publicize the proportion of the students who involved in at least one extracurricular activity is 61%. So here is the equal sign, right? So you have a claim in a non-hypothesis, okay? And then you reject a non, okay? So we're gonna come back to this table. You reject a non, so that's right here, you reject a non. And your claim here is in the what? Your statement or your claim here is in a non-hypothesis. So that is your conclusion. This is your conclusion. That means you have enough evidence to reject the claim. All right. So that means you have enough evidence you reject a non. So what is reject a non? Reject a non, so that means this is incorrect, right? You reject a non, all right? So you have enough evidence to reject a claim. Okay, reject that is 61%, all right? So if you reject a non, that means you have enough evidence to reject school's claim that the students who are involved in this one is 61%. If you fail to reject a non, that means you don't have enough evidence to reject a school proportion in here, okay? So that is how you do this one in here. So basically, you have to look at your claim. You look at your claim in here, all right? So let's look at the car dealer in here. Okay, so the car dealer said the oil change is less than 15 minutes. Okay, let's see. We said the non-hypothesis and the alternative one. Mu here is less than 15, and that is the claim. All right, and then this mu will be greater than or equal to 15. All right, so if you reject the non-hypothesis, okay, if you reject, a non-hypothesis, let's see what do you get. Let me write down in here. Okay, so if you reject the non, okay, since this claim is in the alternative one, and you reject the non, reject this one, so that means this one is incorrect, right? Reject the non, this one is incorrect. So that means the alternative one is correct. Okay, So what is alternative one correct? So that means you have enough evidence to support this claim that the car did the oil change. Indeed, it is less than 15 minutes because you reject the loan. Okay, if you reject a loan, that means the alternative one is the correct one. Okay, so that means you have enough evidence to support this claim, right? So if you go to the table, you reject the loan, right? You reject the loan, so that's right here, and you claim here is in the alternative one. So now look at it, look at this conclusion. You have enough evidence to support the claim. All right, so that is how you do this type of thing. It's a little bit tricky in here, but eventually, after you practice a little bit, you will getting better in this kind of thing. How about if I fail to reject a loan? If I fail to reject this loan, that means I kind of imply this loan is correct. Okay, if I imply this loan is correct, that means my alternative one will be incorrect. All right, so that means you don't have enough evidence to support this claim. All right, so that is in this case how you explain that one in here. Okay. All right, so step to do the hypothesis testing. First, you have to write down the known and alternative one, and then you have to specifically identify your label of the significance. So that means you have a 5% error or 10% error in this kind of thing. And then you need to do the C test or T test, okay? Depends on sigma is given or not, all right? And then after that, you're gonna be able to do a little bit calculation, and then you're gonna be able to say you're gonna reject or do not reject the known hypothesis after you compare the calculation. Okay, so we are not going to calculate tonight because we don't have time left for the entire section, and I don't want to just open a little bit and don't give you enough for the section. All right, so that is the section for 7.1, which is a lot of concept. Okay, I think even more concept than the chapter 6 for this section. But the good thing is if you understand this section, the rest 7.2 and 7.3 calculation actually is much easier. Plus, we also can use the calculator to help as well. Okay, so that is for tonight. Okay, any questions? I know we did cover quite a bit tonight. Okay, any question about you test through or about the one we talked tonight? Anything? Let me go ahead and stop the recording.